Hello, and thanks for joining us. I'm Shannon Sand, an agricultural economist and extension educator with the University of Nebraska-Lincoln's Center for Ag Profitability. Our center hosts these webinars most Thursdays at noon Central Time. Find the schedule of upcoming webinars as well as the archive of every recording at our center's website, cap.unl.edu. Today, we are excited to dive into the intricacies of working with harvest yield monitor data straight from the combine. You'll learn about how to access yield data, the necessary software requirements, and crucial quality control checks to ensure accurate data representation. The webinar will also explore advanced options for yield data analysis and the development of prescriptive measures to optimize farming practices. To present, we are glad to be joined by Dr. Joe Luck, a professor in the Biological Systems Engineering Department and Precision Agricultural Engineer. Dr. Luck holds both a master's and PhD in biosystems and agricultural engineering. He is a licensed professional engineer whose research interests include GIS and data management systems in agriculture, sensors, and control systems, variable rate application technologies, and other precision agricultural technology applications. He also serves as Associate Director of UNL's East Nebraska Research Extension and Education Center near Mead. Joe, thanks so much for joining us today.
Hey, thanks, Shannon, and thanks everybody for joining today. And for those that might catch the recording of this, it's really interesting. So we actually started working with yield monitors back in the early 90s when that technology kind of became commercialized back when ag leaders started out with their precision systems. And so for a technology, that's been around for over 30 years, we still get a lot of questions about best management practices for collecting data, how to process that data. And so it's been a really interesting ride over the years. Just as some little bit of background in this area. So it was really fun. My family farm was one of the first farms in Kentucky back in the early 90s, I think 93, 94, to work with yield monitors, and actually partnered with the University of Kentucky to do some research plots using yield monitors. And then during my graduate work, I actually went back and worked with some of those very professors and worked in the yield monitor test facility there at the University of Kentucky, which was a closed facility where we could do a lot of testing with different things that might impact yield data quality from the operational side. So you'll see a little bit of that stuff baked in here, but it's really interesting that there's not been a ton of change in the basic functions of yield monitors. There's been some new technologies out there, but there's not been a ton of change in how these systems behave and operate over this past 30 years. So it's been really interesting, but we'll get right into it, and I'll have plenty of time for questions at the end. So if you have those, please type them in, and Shannon can help me with those. So tried to prepare this for kind of a wide range of audience, because I know there's a lot of farmers that still ask questions about this. A lot of folks out there that are trusted advisors working with yield data. And then even on the university side, there's a lot of folks that are trying to start to use this technology as part of their research and extension programs. And it's really important, I think, to understand some of the basics so that you're getting quality data. And so one of the first things we'll just kind of talk a little bit about here is what actually goes into creating these yield maps. So, the typical map, like you see here on the right side of the screen, it's a series of points that are collected out in the field while we're harvesting. And typically, it's actually a set of sensors. So there's not one sensor that gives us yield on a combine. It's multiple sensors that are kind of used in a fusion technique. One of the critical pieces of that is what's our logging interval. Typically that's set for 1 second, although in the past we've seen people, do a 2-second interval. But every second that machine is logging a data point, which includes several different attributes to calculate the grain yield in bushels per acre for us. There are a couple of versions of systems I've seen how to do that a little bit randomly. You'll see in certain sets, instead of a point, you'll see a little coverage, box or polygon that represents that. But by and large, the majority of our systems are just generating that point data, which represents, a GPS location on the map. But logging interval is really important. And a couple other things that we have to have is, what's the mass or what's the volume of grain, clean grain that's flowing up into the bin. And we'll talk more about that here in a second. A couple different ways to measure that. Of course, we're talking bushels per acre. So for that acre estimate, we have to have the distance traveled between that logging interval. And that's where the GPS systems today typically come in. What's the distance I traveled from this point to the next point? We look at that times the width, the cut width, which is, either rows harvested in corn or, cut width of the bean header. And that's going to give us our acres. So that dimension and length and width is really important. Again, the GPS has given us a point for that harvest location. Also keeping in mind that we'll talk about this more, that there's, a bit of a lag time between when we cut that crop and by the time it makes it all the way around to either that mass or volume sensor. Finally, the grain moisture, a lot of people don't think about that, but if we really want to look at, marketable yield, we have to correct that for moisture, correcting that down to whatever the current market value is, around 13% soybeans, 15% for corn. And so moisture sensors are pretty critical, but all this information is going into, generating this map that we see here on the right. So the most important sensor really is that mass flow sensor or volumetric sensor. So you kind of see a couple of examples here in the middle of the picture. The impact plate sensor that you see on the left side here is kind of been industry standard for many, many years. We're seeing more and more volumetric sensors where we're kind of trying to measure the volume of grain on these paddles as they move up in the clean grain elevator and dump that grain into the loading auger for the bin. But in either case, the impact plate sensor is going to be located right here in some fashion. Some different companies have different ways to mount those, but we're trying to get, like I said, that impact, the force that grain applies. The more grain we have, the heavier the test weight, the more force that's going to apply on the load cell. If we have some type of volumetric sensor, we have this beam of light laser that's kind of shooting across that. It's going to be located down further on the elevator here, and trying to kind of measure that. One thing I would really say is a lot of people don't think, we've always had that question: how accurate is that one yield data point relative in space in that field? And the answer is it's really not necessarily that accurate. And if you look at this image, I think this is from McClosk's website, that shows the different elements of grain as it moves through the machine. You can start to get some appreciation for, if I cut that crop, if it's soybeans or wheat or whatever you think about it, and it starts its journey, across the header up into the throat of that combine, and then it starts to move into the rotors where we start the grain removal process. You can start to appreciate that as the grain moves along these sieves, as it moves further up into the machine for cleaning, it's again coming down more sieves. There's several different routes that grain might be able to take to go through this machine, again, as it's continually moving down and being cleaned and processed, to where it moves to the initial, cross auger that's going to start loading that clean grain elevator and dump it into the bin. Some of this material might get caught in the tailings elevator here and actually get dumped in back up here for rethreshing. So, for better or for worse, that one point out there, could represent quite a lot of area around it, not necessarily that exact area or that exact, cut area that we made. So just keep that in mind as you're, working with and using yield data. We've had a lot of people over time say, well, I put out this 50-foot plot or these series of 50-foot plots, and we're pulling that couple of yield data points out of that plot, and unfortunately it may not really represent what's contained in that plot just because of how grain moves through the machine. So We do have a setting for that. Most of the time it's automatically preset, but that lag time from the cut to when the majority of that grain starts to hit that, hit the bin through that loading auger, we back up a second or two to get the time where it actually hits that impact plate or maybe clears that volumetric sensor. So we try and accommodate that for some, but again, just appreciate that the grain could take a lot of different routes to go through this machine and end up in the clean grain tank. So it's just something we have to deal with. The first thing I always tell people is calibration is really important, although it can be a little bit time consuming because calibration affects every single yield data point that you collect out in the field. Typically, my recommendation is try and use manufacturer specifications. Each season, perform new calibrations if you can. A lot of people will try and go and do a quick check if they've got a load cell on their grain cart or something to see if they're close. But things can change over the year, and new calibrations are always beneficial for best quality. We have to have different calibrations for different crops. The way the seeds impact the plate can affect that the data quality. If we have a lot of difference in test weight or moisture content, that can also require calibration. So back in the yield monitor test facility days when I worked back there, we actually tested, we calibrated the machine with one variety of corn. It might have had a test weight about 56 pounds per bushel. Then we would bring in a new load of corn that had a test weight, maybe 61 or 62, and run the machine to see how accurate that previous calibration was. And it would throw off the results by about 2%. So that 2% can add up over time. And so, if you have that wide difference in test weight, it would be worth thinking about doing an extra calibration if you can. Moisture, and a lot of people see this in soybeans, but soybeans can really dry down during the day. Pick up moisture later, maybe. And that's just been a frustration a lot of people, and there's not a lot we can do about that other than just doing our best when we're running that calibration to get something that's going to be right in the center there. One of the things that makes the most difference in terms of yield data quality from a calibration point is, we'll talk in just a second about how to generate that calibration, but really the thing to think about is, what do you think the lowest flow through the machine is going to look like? Not the extreme low, but for instance, if you had down corn, you're going to be driving much slower through that field. So the flow through the machine is going to be pretty low. What's your expectations of a really high flow through the machine? And so, best yielding crop, moving at your typical maximum speed, what's the flow through the machine look like? And if we're doing a multi-point calibration, which is typically what we recommend, we try and span that range somehow with our different calibration loads. When you're collecting those calibration loads, a lot of people forget that each load, and I'll show you this in just a second, really only takes about 3,000 to 5,000 pounds of grain. It's not a truckload. It's not 1,000 bushels necessarily. The goal is to get in there, get a quick calibration load. You'll see it says maintain stability. So while you're getting that 3,000 to 5,000 pounds, just being as consistent as you can, get that and stop it and weigh it. That's going to give you the best data. So if you're just imagine you're averaging in, if I go 1,000 bushels, I'm doing multiple bin loads, the grain, while it's calibrating, the flow through that machine is going to continue to go up and down. And it's trying to average that in for that load. Whereas if we just have really short, very consistent flow while we're getting that calibration, it'll give you the best results. And this is kind of a way to visualize this. If you think about what the flow sensor outputs here, and this would be an example from some data from an impact plate system that you see there. If the flow is low, we have a voltage output. And as the flow increases, that voltage output increases. And the problem has been over time, it's not a really linear relationship. It can be approximated between these for multi-point calibration, but that's been one of the big problems in the past, is that relationship has a bit of a curve relationship here when we're looking at actual mass flow through the system. So this is some of the data from the yield monitor test facility back then, where we could actually measure that versus the mass flow through the system. Our goal is, again, thinking about a lower flow through the machine. So this might be my lower yielding areas. This might be my higher yielding areas. Again, think that, your travel speed and the yield are the two big things affecting the flow through the machine. Obviously, cut width is important, but there's always been two ways to generate this curve. Either one, you set a constant speed and then you change your cut width to kind of generate those flow regimes through the system, or you maintain a consistent cut width and you're just changing your speed for each one of those calibration loads. So again, each one of these red dots you see here would be a calibration load, and again, maybe 3,000 to 5,000 pounds maximum for each one of these. So if I'm running in high moisture corn, I get out in the field and I'm like, well, if I think my lower yielding areas might be, 150, 180, my higher yielding areas might be 270, 280. I'm trying to, capture those here and then adjust accordingly. So that's kind of the basics behind how you might generate that. But again, this should be done for every crop. If you're moving from a high moisture corn where you're up in the 20s, you're getting into lower moisture where you're down around, 16, somewhere in that neighborhood, I would definitely recommend doing a different calibration, because you'll see that definitely errors going to accumulate there. So a couple of other sensors we talked about that are really important here is moisture sensors, obviously, are critical. The common style you see here, unloading off the clean grain elevator, it takes a couple of seconds for those to get a good estimate, and then it's kind of dumping that and then monitoring that. And actually, these type of sensors are very accurate for most of the grain that we're in. I would always double check and make sure they're good and clean. Every so often, when you get into some wet harvest conditions, sometimes you can get some material buildup there. But if we want to know how much grain we've got for market, we got to know the moisture content. One sensor that a lot of people don't think of is the header height sensor. So this has been kind of in the past, the most popular type of sensor, where we're really just looking at the movement of the throat of the combine up and down. So we're setting a limit on that says if I pick it up past that, I'm going to stop logging yield monitor data. And you kind of see here what happens if you don't have that sensor set up, or maybe you just, you say, well, I'm tired of raising the header up. I've got it at a nice height. I'm going to, just make that turn out in the headland and come back and not touch it. And this is what you might end up with. And we'll talk about how this could affect the yield data quality in the long run. But you can clearly see here that, either this header sensor was malfunctioning, or maybe the operator just wasn't raising the header up enough to get that sensor to kind of indicate that we're not harvesting. And it's really important, to try and get that as close to when you're actually harvesting the crop and when you're finished harvesting the crop, because that's going to affect your area, because the system's trying to log harvested area while you're doing all this, and that can affect that, as you can see here. Another one that's really difficult to control, because there's things out in the field, where I grew up, we had a lot of old clay tile out in the field. So, you might be driving along and have a 4 or 5 foot sinkhole. You have to stop. But just realize that, when you're accelerating and decelerating, that's going to affect the distance traveled. And even though, GPS systems are quite accurate, we've got that lag time setting in there. It's really hard for that system to compensate for that change. So you can even see in this example here on the right, where, you can kind of look as the machine was moving along kind of from east to west here, you can see the gap between those points. Well, they had to stop suddenly or slow down suddenly, and then they kind of take off again. And you can see what the yield estimate actually was able to isolate this one point, where it estimated a 1,600 bushel per acre for that one point. And we'll see here in a minute how, that if we leave that in there and just maybe take this data and create a grid or create a zone map, that data point will actually affect the ultimate value of those different cell sizes, and not the cell size rather, but the value of that cell. So this is something we have to be really careful with. It can affect our results or some further. But again, just remember that the distance traveled, times the cut width gives us that harvested area. And if the machine can do a lot, but if it can't really compensate, if I'm dividing by a very small area value, it artificially inflates the on this. So I'm just being as smooth as possible. Again, it's sometimes when you're looking at looking for the bottom of a sinkhole and you can't find it, you're going to have to stop or it's going to be worse. So sometimes you have to do what you have to do. So kind of transitioning to looking a little deeper into the data. And there's a lot of different software packages. We typically call them farm management software. And I apologize, but there's so many of them out there now that it's almost getting difficult to keep track of everything. But the ones that we deal with the most with folks, we're obviously seeing a lot of people using Operations Center from Deere. Climate is another one that's online that a lot of people are using. SMS Advanced from Ag Leader, still extremely popular. It's a desktop software, but it's got that cloud connectivity in there. There's other ones, Granular. I can't actually list all the ones that are out there anymore, but a lot of the data that's being generated today is automatically moving to the cloud. So you take your Deere machinery, Case, AGCO, any of them, and the cellular service is transferring that data up to, say, Deere Operations Center, or it's transferring that up to Climate's data center, and you can access it there. There's still a lot of folks that still have to pull data off the monitor manually. So, we think about a jump drive or a thumb drive. You go out, you insert it, you transfer your harvest data over to that thumb drive. And then, the problem a lot of people have run into in the past, and this has been a really common issue for folks in the research side of things that aren't used to this, most of that data is encrypted. So if you have your jump drive, and one that I'm using actually right now, it's one of the Nebraska, thumb drives, but the data on that is typically encrypted, and it has to be, unpacked or unpackaged by some software that's capable of doing that, to get it into some type of format that you can work with without special like farm management information software. So the easiest example I can give you is a lot of folks that we talk to, if they're still in that boat, they might have a Ag Leader SMS basic package where they can take that data, plug the thumb drive in, import it into SMS, and then and once you have it in that software, then you can export it into other types or other formats, maybe a shapefile or a JSON, GeoJSON, something like that might be useful. And I see that a lot of researchers doing that. If your data is automatically going up to the cloud, typically you can export from those cloud-based systems in one of those formats. So it takes it one step out of the process. There are some folks out there, for instance, I think USDA is working on this, ways to help people out with that. But that's been a barrier that a lot of people need help getting around, is, I can pull the data off the system, but then how do I get it into a format that I can actually do something with? So a couple of things I always tell people, thinking about what your goals are for this. So I'll go through some examples here next, showing you how we've used some of this for spatial analysis, and a lot of different outcomes you can get from that. But really, I think one really important goal for folks is just benchmarking. We've got the ability to log this data spatially, and if you can get a few years of that data built up, it's really going to start to show you areas of the fields that you may need to pay more attention to. And, for instance, some fields back in the area where I grew up, a lot of times it's drainage issues. So, we see variability in the yield map and automatically think, I've got to do something variable rate here. And back in that area, a lot of people, it might just indicate areas of the field where they need to put some field tile in or something to correct a long-term drainage issue. So just having that multi-year set of data, it takes into account the temporal variability. So year to year, what are we seeing differences in weather? What are stable areas of the field versus areas that are, varying a lot? Those are some of the things we can learn by benchmarking, and just having a good yield history is really important, and it helps out in a lot of the prescriptive things we look to in the future. So for instance, people that are looking at maybe doing nitrogen prescription maps really recommend, if you're going to use yield data, have at least 3 to 5 years, if you can, just to capture that variability, so it helps you with those ultimate prescriptions. But those are just some things to think about. One of the key steps I've kind of alluded to, though, is the quality control. Again, it can be challenging to go through and look for these errors that you're going to see, and you will see them in yield data. There is free software from USDA. In the past, we've done a lot of training on this type of stuff. We've actually got some online courses that are out there that people can access and learn how to use this software. For instance, it's called Yield Editor. The biggest hang up there is, at the moment, it only accepts data that's been exported from SMS. So if I pull my yield data into SMS software, I can export that and use USDA Yield Editor. But it's really nice because it automatically goes through and searches for a lot of these errors we talked about, particularly the acceleration, deceleration. If you've got cut width errors, we'll talk a little bit more about that. It can automatically work on those. You can, in some of the commercially available software, you can actually go in and build filters in. So again, an example in SMS, you can actually go and build in filters to try and tease out some of these errors. Maybe the acceleration, deceleration error, you can actually do that by selecting different speed changes. So some of this stuff can be automated in the technology software that's out there, which is really helpful. And I would just say, I've had people argue with me about this. Statistically, is it valid to remove data from the data set? If we always recommend people save the raw data. So always try and have a backup of your raw data files. But, if I'm using, I'll show you in just a minute here, if I'm using this data to assess a trial or maybe create a prescription for the future, in my opinion, absolutely yes. If we know those errors are physically caused by the system, we have to take them out if we're going to use that. Otherwise, you'll see what will happen here in just a minute. So here's just another couple of examples we'll talk about, just thinking about the quality side. The map you see on the left is a raw yield monitor file. You can actually start to see some of the errors pop out. You see things that just don't look natural, things that are artificial. So these little red strips right here along these point rows, basically harvesting into the point rows, at that angle. And if I have a system that's not automatically adjusting my cut width, and I don't change that cut width, the cut width can be a major error, and that's what you're seeing here. Again, if we have a 40-foot header and we're getting down to the point where we're only harvesting 20 feet, that's 50%. So if that's not adjusted, it's going to just become that much of an error. So some of the systems, it's really been interesting to see today. We've had section control for sprayers and planters where we're basically mapping what's been, planted or sprayed in the past. These companies have kind of flipped that around and said, well, I can use that then too. If I know where my header's been harvesting and the header's not been harvesting, I can actually use that same section control technology to map out where I've harvested crop before, and they can automatically adjust cut width that way. So that's been really interesting to see. But if you do a quick filter on some of these data, you start to see where a lot of these errors pop out. This actually an old yield map from home, a soybean crop, and I would love to tell you that we could harvest 180 bushel soybeans, but these values, anytime we get over 60 to 65 bushels per acre, and in this part of Kentucky, there's just no way that the values are that high. So you can see, there's actually one point out here somewhere that's 181 bushels acre. It's one of these whites. And you see a lot of these values here along the headlands, header up or down, point rows that are causing those errors. So I kind of highlight those here. What I would say was I've actually heard people in the past say, okay, well, I'm going to take that map that you see on the far left, and we're going to clean all that up by creating a grid or a zone map. And I would just say that those values, if you're just clicking a button to do that, those values are still in there and they still affect the yield. So what I did here was I actually looked at the difference in yield. So if I go to a 50-foot grid that you see here on the right, this is the difference between a map that's generated from the raw data and a map that's generated once I remove these known errors. And you can see some places out there that difference is 20 to 30%. So if you look along these point rows here, we're estimating yield anywhere from 10 to 20%, in some cases less than what the actual yield was. So these are some of the things we need to be thinking about in terms of data quality if we're going to use this long term. And so that just kind of highlights what some of the possibilities are. Just another quick rough example here. Again, this could be a header height sensor area that you're seeing on the left. It could have been the operator just not picking the header up high enough when they enter and exit crop. But if you look to the far right there, you see again, if I create this gridded map, about 50-foot grid with that raw data file, and then I create one with the cleaned data file, and then I difference those two, you can see along the east side where all those headland errors were. I'm 50 to 90% off in those yield estimate values. And the danger here is today, a lot of this data can be processed in batches where nobody's actually taken a look to double check that, these type of errors aren't being taken out of the file. And so that's the danger. We just need to make sure we have some type of quality control check in there to validate that. And this is one example, I used to do in the site specific crop management class, where I did basically the same thing we've been talking about with thinking about spatially varying nitrogen based on yield map as one input. And if I do that with a raw map, and I do that with a map that's been processed and remove some errors, you can actually start to see where some of those start-stop errors in this field. So you see this red boxes, that's a 15 or more pounds per acre increase in nitrogen that was probably just caused by an overestimate of yield. So again, there's a couple of points right in the middle here somewhere that the operator had to stop really quickly. It generated a super high value for yield. Probably I've seen up to 3,000 bushels per acre, for corn, which is, a fine goal, but not legitimate. And so something like that is affecting those cells. You can see those dark blue areas, which are likely point rows, where again, we've kind of the value of the yield in those cells has been artificially deflated. And you can see that it's affecting maybe a future nitrogen recommendation, up to 10%. I think the average for this field was around, 150 pounds per acre. And so we're seeing places out there that are greater or less than 10%. So just think about that as we continue to move forward in these prescriptive analyses, how we need to be keeping our eyes open for data like that. I think, these errors, we've really got to get a handle on that before we move too much fully into the digital space. So what I'll do now is go through a few examples of what's possible. And some of these analyses that I'll show you, we've done in just a commercially available farm management information system. I've seen others do this type of stuff. Climate, I think, is getting really good at showing some of this. We've used AgLeader SMS a lot in the past. Some of the analysis we also pull into more of a generic geographic information system. And that's where that kind of removes the whole management side of it. It's just focused on spatial data and analysis. And so those are some more basic ways to do that, I say, where it's actually a little bit more challenging to do a lot of that programming, but get really good information. But what are some ways to use this data? Well, here's a file. So what we're looking at here on the left is the grade, the slope of this field, a really high area here in this region, then kind of moving down into a sloping, flatter area where terrain's kind of flattening out and catching a little bit more moisture. You can see that this was basically a split planter study where we had two different hybrids, a defensive and an offensive hybrid, thinking about water availability. And then you can see the yield map here on the far right. This was in a drought year. Unfortunately, a drought year, but a really good year to look at some data between these two different types of seed. And so what you kind of see here is this was again done, I think this was done in SMS from Ag Leader. You can actually see the relationship in terms of yield change as these two different hybrids kind of move up the slope from the really low-lying area where the offensive hybrid did fairly well up into this area, which had a lot less moisture availability, where in that part of the field, the defensive hybrid did well. And you can kind of see those tighten up a little bit, but the transition's still there. So some information you can get is not just maybe the product or the rate and that impact on the yield, but you can also start to look at those natural variabilities, slope, soil texture. We try and capture that a little bit better with things like electrical conductivity, but soil texture, you can definitely get an idea of how these different hybrids would have performed in that scenario. This is another example. A fantastic graduate student worked with this a few years ago, but we were looking at not just different products from the seed side of things, but maybe seed treatment. So we had access to a multi-hybrid planter. And this year, Rachel, the graduate student, built these prescriptions kind of based on historic yield observations in this soybean field that had a history of sudden death syndrome. And so with that planter, we went out and were able to insert those different treatments. So what you're seeing here is, this white area is got a history of sudden death, more severe. So we're actually putting in blocks, because that multi-hybrid planter, we can put in an untreated seed and a treated seed, and then deploy those out and collect this data. You can actually start, if you look in the yield map, you can pick out some of these blocks where we had that, and we could actually validate some of that with aerial imagery as well later in the season. But just in this one example, if you were able to optimize the placement of that Elevo, and not everybody's going to run out and grab a multi-hybrid planter for this, but even just thinking about, if I put the treated seed in and planted and then transitioned over to an untreated seed, but if you could actually match these zones up, it could have improved profitability by $80 an acre. The soybeans responded that well to the seed treatment in that zone. So it was showed a lot of potential here for, what we would say those really persistent issues like sudden death syndrome, to be able to correct for that and save a little money in parts of the field that don't have quite so much stress. A lot of opportunity there. So, and I think that's one of the keys, is really identifying those issues that are persistent year after year. So talked about having multiple years of yield. It can show you those areas that are consistently off for some reason and give you an idea of where to target, some type of approach. Again, here's another example of a corn hybrid assessment. Two different hybrids, just planted a split planter across the field. Again, this analysis was done in a commercial software, but you can kind of see here a zoomed in version of how those yield data points align. And the key here is making sure your application equipment and your harvester line up well. So, this was an instance where the farmer had, half of the header, half the planter represented one header width. So he was able to get two passes. And then we could actually get a lot of replicates of this too, which is really important, but really to determine what the what hybrid outperformed here in this field. Another interesting example here on the right side of the screen, where this study compared two different hybrids, and unfortunately, one of the folks that had the weigh wagon and one particular hybrid kind of bailed out on the results, but we were actually able to go in and pull the yield monitor data, and you can start to clearly see where one drought tolerant hybrid was outperforming another drought tolerant hybrid based on where those red strips are cutting through. But if we didn't have this yield monitor data, that study would have been a bust. So there's a lot of usefulness here, I think. And one of the things you'll hear me talk about a lot is on-farm research. I think it's one of the best ways to make use out of these technologies. We'll talk about some best management practices here, but really two key terms to this for me are randomized and replicated field trials. So this is an example of a seeding rate study that an operator did. I like the division and the seeding rates, 30, 36, 40. It's a wide range. When we go back and look at the machinery giving us the as applied rates, you can clearly see there's a good division. If we only varied it by 1,000 seeds per acre, we might not have seen very much. But what you see are six blocks out there in the field. Each block has one of those seeding rates, and they're randomized across the field, so they're actually mixed up in order, which helps. If we had some type of spatial variability, say that the yield was really low on the west side and it just always increased up to the east side of the field. Well, if you have all your seed rates in the same order, one of those seed rates is always going to be on the low side and one's always going to be on the high side. So randomizing those and changing that really helps to tease some of that out. We had 6 blocks, so we're actually able to do some statistical analysis on the data. You have to have at least 3 replicates to do that. And I like to use this example because there were a few yield monitor data errors we picked up in this data set. And if you use the raw data, what you find is there's really no difference between those 2 seeding rates in terms of profit potential. So if you look at the yield and then the amount of seed and the cost associated with those, once you go in and look at that yield monitor data and you actually try and remove some of those known errors caused by the machine physically, you actually start to see that information become statistically different, because we were really underestimating yield in that 32,000 seeding range. And as it turns out, it ended up being potentially more profitable. The other thing I always tell people is when we're laying out these studies, notice that in 2 of the blocks, the 36,000 seeds per acre actually had the highest partial profit. If we look at, the yield and then the cost of seed. And if you look at this block number 6, the 36,000 actually would have done better than the 36,000. So this is another reason for trying to have multiple replicates of these treatments or these blocks out in the field. If I'd only picked one of these, I could make a bad decision. So that's really helpful here when we're trying to set up and design these studies. Again, I always think that benchmarking is really a huge benefit for these systems, identifying that spatial variability over time, looking at areas that are persistently low or needing attention. But really, for me, I think the on-farm research, which we've been working with yield monitor data ever since I came out to Nebraska about 12 years ago. If we can really ensure quality control in these field studies, we can use precision ag technology and yield monitors to validate that. So here's an example of a trial that's going to go on for a few years here at our research farm near Meade at ENREEC. And you see on the bottom left here, we basically built a prescription that we can load into the anhydrous applicator, and the applicator goes out and puts those in, and the operator doesn't have to make any changes. We actually have an in-season approach. So what you see here in these treatments are, you see a 0 nitrogen treatment followed by 4 treatments of anhydrous, including 80. So that's 120, 160, 200, and then this 80-pound treatment up front in the spring with anhydrous. And then you start to see the split approaches. So we've got, 80 pounds of anhydrous around B12. We go in and supplement that with UAN and some additional rates. So again, when we do that UAN application in season, we have this prescription map. We push over to that, and as operators moving across the field, that can be applied. And then we're using as applied data to try and validate what went where, and were we within a pretty good percentage, because as most of you have experienced, and even yield monitor data, like we talked about, those values don't instantly change based on this line that you see across the field. When it comes to nitrogen, the application equipment, we try our best to tune those to respond quickly, but sometimes it takes 20, 30 feet out into those plots before we actually hit the rate, especially, if we're going from 200 down to 80, between 2 blocks, it takes extra time. So we recommend people, if you're going to design these plots, really for about 250 feet, because you can go in then and trim off some of those edges. If you can get about 200 feet of yield monitor data, studies in the past have shown you really need that because of the yield data variability. We talked about how those, the flow through the machine, and that can take different paths. You really need about 200 feet to get an estimate that's going to match up really well with the scale weight. And that there's just been a lot of studies in the past that have kind of validated that. So anyway, that's kind of how we're using this to try and maximize our field area. So we'll get 6 replicates of each one of these treatments. They're out there across the field. And so there's gonna be a lot of good data that we get out of this field study. And again, if you can think about, validating that, take a look at the as applied data to make sure things kind of went in where and at what rate you really expected. So we can do this. We've actually done some of this with a typical farm management software, like an Ag Leader SMS. I know a lot of people have shown me with climate how they're able to pull some of this information. What you're seeing here is a map of the data that's been pulled into GIS software. In this case, it's ArcMap, which it just lets us dive a little bit deeper into the analysis, but can be challenging to operate. So those are all the prepared slides I had. I noticed, I think, a couple of maybe a question. I don't know if it popped up or not, Shannon, but I guess let me know and I can jump back anytime here in the presentation and try and help address those. So.
Okay, so we do have a question. It says, for yield monitor calibration, why is the line curved rather than linear, and what causes the curve?
That's a great question. I think it has to do just with the way those historically those load cells have been set up in the equipment. But it's been really interesting to see actually going in and collecting the raw data from those. So I'm not sure. I've never been privy to any of the manufacturers, behind the scenes, what's going on there, but I would say that's fairly typical with a lot of these, not a lot, but some of these electronic systems. There's just a nonlinearity sometimes in the output. And, there's been a lot of companies, and I guess I think I can skip ahead here quick. There's been a lot of companies in the past that have tried to try and use less calibration loads, which in some ways can be good. So this is some of the similar data that we pulled. You see that same kind of nonlinear output.
Yeah.
With a 2-point calibration, you can actually start to see where I'm overestimating and underestimating. If you look at the error here, so this is actual data from the facility. This is my 0 error. You can almost point where the calibration loads were generated. So they were generated around these 2 locations here. That's where our lowest error was. And when we got between those, when we got outside of those, you start to see the error really increase. When you look at a multi-point calibration where it's more of a piecewise, and this is what I think was critical to ag leaders' success back in the early days. When you can break that down, you see the error is actually fairly consistent. It's increasing a little bit above zero, but on average, it's pretty consistent. So I don't know. It's a weird artifact. I don't think we see quite the same with the volumetric systems, but remember, volumetric systems we're actually calibrating these back to weight. So even with the volume-based systems, you're running a calibration load and you're weighing it. So that makes that one a little bit more complicated, in my opinion, because of the test weight. Only other real quick thing I would say there is technology like active yield from John Deere. A lot of folks are seeing that out there now, where the bin on the combine has some load cells that are capturing calibration weights. We've heard that. I've experienced it personally, but colleagues that have worked with those systems, really good if you're just trying to get a quality yield map. When you start to get into the research plots like we showed you before, where you're going to start to expect pretty wide swings, they've actually found that disabling that active yield, getting some manual calibrations, has given them better data in these types of environments. But from a production standpoint, I think active yield has been a great thing for just improving overall yield map quality. So
nice. Okay, we have another question. Would you be comfortable using yield monitor data to determine flexible rent?
Say that again. It broke up just a little bit.
No, yeah, you're fine. Would you be comfortable using yield monitor data to determine flexible rent?
Flexible rent? So as in like rental rates on
That's
on
kind
a
of
field?
my assumption. Maybe they can type some clarification into that, but that's my assumption on it as well.
Yeah, that's a good question. I mean, I would say potentially. What we try and tell people is, historically, if you can get a yield monitor, the number has always been 1 to 3% on an average field, so probably 20 or more acres, is a really well calibrated yield monitor. And to me, if you've got a fairly well calibrated monitor, the variability across the field should be fairly consistent. The only thing I would say, so you're going to see a nice variability in the spatial yield. I think those values are probably pretty consistent with each other. The thing I would say is absolute yield can be a problem, because I mean, you got to think back to your calibration. So am I 100% sure that one area of the field was average, 150? It's going to be 150 plus or minus. The one thing I tell people is, if you don't have a really good calibration, if you've been able to perform this kind of calibration, I have a lot of faith that those relative values are going to be pretty close. If you have a calibration where you have error like this, I don't have that, because basically everything that's overestimated, I'm skewing more, and everything that's underestimated, I'm skewing more. So that's the thing you have to really think about when how calibration can affect an overall yield map. So
okay, sounds good. Do we have any other questions? We have a couple more minutes, but not long. So all right, well, I'm going to ask a question real quick. Joe, do you have
sure.
Do you have resources that you recommend for people to go to learn more about this, and like how to do their own calibration and things like that themselves, as well as like look at, begin benchmarking basically? So
Sure, we actually do. We've actually put out a couple. They haven't been updated in a while, but we actually have a couple of extension circulars through Nebraska Extension that talk about yield data collection, talk about quality, post-processing. And then I mentioned the digital ag team has put together some online learning resources, and it's through Teachable. So if you Google Teachable digital agriculture, you can enroll in these courses for free. We have one that just talks about kind of the basics of yield data, how to use that yield editor software. and we have one that talks about basics of ag data management, and then we have one that's actually on performing on-farm research with yield data. So
nice. Very good. Very good. Well, if there are no other, oh, we do have, it looks like precision farming methods using yield monitor is acceptable for reporting a yield crop. Okay, someone was answering, I think, here. This was not a question.
well, they are, as we're starting to learn the RMA and FSA, they're starting to accept different types of precision ag data, the as applied planting data, for example. I think they're going to start using that. So yeah, it's been interesting to see those advancements. This was what I was going to share with you real quick. So if you go to that website, you can actually see a couple of the different courses that we've put together out there that kind of take you through some of the steps to learn about those different technologies. So digitalag.teachable.com.
Oh, nice. Well, thank you everyone for joining us today. A recording of the webinar will be posted at cap.unl.edu, where you can also register for other upcoming webinars. We would also really appreciate your feedback on the brief evaluation that should pop up as you close out of Zoom, and that helps tell us how today went and inform us of future webinars. Thanks again for joining us.